Hello and welcome back to A Slice of Physics. We have talked about the speed of light and we have mentioned that it's a constant across all wavelength and frequency. But that doesn't mean that it's a constant across all materials that light passes through. So in this video, we're going to consider that question: is speed of light constant in all materials? The answer is no, otherwise I wouldn't be making this video. And if it's not constant, we will talk about how it changes, whether the wavelength or frequency is affected, or both are affected, and then how the index of refraction is related to all this. All right, to start this discussion, let's talk about speed of light. Generally, when people talk about speed of light, they think of this constant called c, which is 300,000 kilometers per second, or 186,000 miles per second, or 300 million meters per second. This is the speed of light in vacuum. We generally don't say that, and if we don't say that qualification, it's in general implied. So that's the speed of light in vacuum. Okay, so when it's traveling in interstellar space, that space is pretty much vacuum, so that would be the speed of light. When it gets into our atmosphere and light as it travels on the surface of the Earth or near the surface of the Earth still travels at a pretty similar speed to that. So speed through air is roughly 299,900 kilometers per second. So it slows down, but just a tiny bit. But then if you send light through glass, then it slows down quite a bit. It depends on the specific type of glass, but roughly it'll go down to 200,000 kilometers per second. Still pretty darn fast. That's about 124,000 miles per second, not per hour, but per second. So it's still pretty fast, but it is considerably slower than the speed it travels in air or in vacuum. So in general, we consider these two things to be roughly the same, but we also note that the speed of light is lower in different materials. And by the way, this constant c is reserved for the speed of light in vacuum. So anytime you say c, the lowercase c, it is the speed of light in vacuum. It has this specific value. We're not talking about the speed of light in any other material. So when we talk about the speed of light in other materials, we can't use c. We just have to use v, which is a general symbol for speed. But here I'm talking about the speed of light through these materials. Okay, we also mentioned that speed of any wave equals the wavelength of that wave times the frequency of that wave. If you remember, since I'm a runner, I like to talk about my speed as the wavelength of running, which is the stride length, times the frequency of running, which is generally counted as cadence, the number of steps I take in a minute. So if I want to go faster, I got to turn my feet faster, increase the frequency, or I got to increase the wavelength, make my strides longer. But for light, we couldn't do that. Light going in vacuum of all wavelengths had the same speed. So as wavelength increased, the frequency correspondingly decreased, and so on. But now we're talking about speed of light changing. So if light is going from vacuum to glass, let's say, we've already said that it slows down. So how does it slow down? Is it because it reduces its wavelength, or it reduces its frequency, or maybe it reduces both by a certain amount so that the product also reduces? Well, the answer turns out to be that the frequency, the number of times the electric and magnetic fields oscillate, is not affected when light goes from one material to another. But what is affected is the wavelength of light. And that's because the electric fields in the electromagnetic wave have to interact with the electrons that are in the material that it's going through. And that interaction slows them down and reduces the wavelength. So if I have a wavelength of light, it's happily going through vacuum, and then it enters a slab of glass here. So when it enters the slab of glass, its wavelength will reduce. So I'm going to exaggerate it here just so you see what I'm talking about. So outside, the wavelength was from here to here. So this was lambda in vacuum. And inside in the glass, the wavelength is from here to here, lambda glass, a smaller amount. Frequency remains the same. So let me make a note of that. Wavelength changes when light goes from one medium to another. Frequency remains unchanged. And since speed is just the product of wavelength and frequency, the speed also changes. I haven't said reduces and I've said changes because if you're talking about going from glass back to vacuum, then light is going to speed up. So all I'm saying is lambda changes and V changes accordingly, but frequency remains unchanged. All right, so we define a property of the material that tells us how much light slows down inside that material. Property of material that quantifies the slowdown of light in the medium when compared to vacuum. And that property is called the index of refraction. In a future video, you'll understand why it's called the index of refraction. But let's just tee it up now and define what it is. So N is defined as the speed of light in vacuum divided by the speed of light in the material. So I can write this as C. C is the speed of light in vacuum divided by V for that particular material. So since the ratio is defined this way, C is in the numerator, C is the biggest thing you can have. Light travels faster in vacuum than in any other material. So for vacuum, N will be exactly 1.0, okay? For air, N is approximately 1.0003 near the surface of the Earth. So that's why we said it hardly slows down. And by the way, these three horizontal lines here are used when it's by definition. And in this case, since the numerator is always C, and when you use vacuum for the material, the denominator will also be C. So I'm just showing it as a definition. It's not technically a definition, but it's precisely 1. And then for glass, N is approximately 1.50. It kind of depends on what specific glass piece you have, but approximately 1.5. So we've noticed something here. N is 1 is the lowest possible value that it can have. For anything but vacuum, N is going to be greater than 1 because the speed of light through that material is going to be less than the speed of light through vacuum. So you're going to be dividing the numerator by a smaller number than the numerator, which will result in a number that's larger than 1. By the way, when we do slow down light enough and then we have other things going faster than light through those material, there are some interesting visual effects that happen, but I don't have time to talk about that in this video. So the other thing we said is frequency doesn't change and wavelength changes. So I can rewrite this as N equals C over V. I'm leaving out the subscript of the material, which will also be equal to the wavelength of light in vacuum divided by the wavelength of light in that material. That's because C would be equal to wavelength of light in vacuum times the frequency of light in vacuum. V would be equal to wavelength of light through that material. Let me go ahead and write the subscript here. Times the frequency of light through that material. And since we said that the frequency doesn't change, I don't need to use these subscripts for frequency. I can just simply say F. And by simply dividing these two equations, I can get the relationship that C divided by speed through that material equals wavelength in vacuum divided by wavelength through the material times F over F. The F all cancels. So the ratio of the speed is equal to the ratio of the wavelength, which is defined as the index of refraction. By the way, if you're wondering if the wavelength of light changes when it goes from one medium to another, will we perceive that as a change in color? Well, it so happens that our perception of color is related to how much light there is and what the energy of that light hitting the rods and cones in our, more specifically, I guess, the cones in our retina are. So that energy is related to the intensity of light, which is why when things get really, really faint, you see them in a different color, or you don't see much color definition. But if you have the same intensity, the frequency is what interacts with our perception mechanism. The wavelength does not. So luckily in this case, since the frequency is not changing and that's what we detect, we don't detect a change in color when light goes from one medium to another. We simply just detect a change in speed. All right, so let's recap some of the main things we talked about in this video. So the speed of light does change when it passes from one material to another. We reminded ourselves that the constant C is the speed of light in vacuum. And by the way, it's also the speed limit of the universe. Nothing can travel faster than the speed of light in vacuum, according to Einstein's theory of relativity. And when speed changes, we said the frequency remains the same, the wavelength changes, and so they both change by the same ratio. And then index of refraction, this n, which has no units, is defined as the speed of light through vacuum divided by the speed of light in the material, which is the same as the wavelength of light in vacuum divided by wavelength of light in that material. Thank you.